Hi everyone and welcome to another lecture. We want to talk about basics of bracket algebra today. So let's say I have a ket vector represented at okay, let's cross it. I have a ket vector v written as 1, 2 plus I and let's say 0. And I have another ket vector written as w which is 0, 1, I. So it is similar to adding of two column vectors, and in the bracket notation we write it like this. First we write ket v and then we write ket w, and you just add component with components, one, and you write the final result, that is 3 plus I, and this is just 1. So this is how we represent. Here you can see the ket of v plus ket of w, and the representations are the column representations, and the rest of the algebra is similar to the matrix algebra we saw in our week 1 lectures. Similarly for bra, let's say I have a bra called A as 1, 0, 0 and another bra of B, it looks like an L, and it has, let's say, 0, 1, 1, and if you want to add them you have to write it like this: 1, 0, 0, 0, 1, 1. This is just 1 plus 0, that is 1, 0 plus 1, that is 1, 0 plus 1, that is 1. And you can even call it a bra vector C. And for scalar multiplication, let's say A is some scalar that belongs to, in general, any complex number. So A of capital A prime, this is just another ket vector, is the same as A small a times capital A prime. How we can see this? Let's say you have A small a equals to 2, A prime is equals to, let's take a 2 entry column vector, that is 1, 2, and then A of A prime is just 2 times 1, 2. You have to multiply by 2, but then again this is just A prime, right? That is how we can write scalar multiplications, and this is also a property. Similarly, we can write A prime of, let's say, bra vector B equals to A prime B. But here you have to be careful that which one is the scalar and which one is the vector itself. That is, which symbol or which alphabet you are using to represent the vector. Now we have seen this addition and scalar multiplication. What about a vector multiplication? This will be very important for us, the thing we are going to talk about now, vector multiplication. By this vector multiplication I mean I have two vectors and I want to multiply them. I want to multiply them. Now how can we do that? The next question is, how can we do that? Well, it depends on what what you want out of these vectors. Let's take an example, and we will generalize this kind of things when we talk about vector spaces formally. Let's say I have two vectors, that is one A, let's write it as 1 plus I, again 0, and B as I, 2, 0, and I want to multiply A and B in such a manner so that the result let's say the result will belong in a complex number. That is, I want to extract out a scalar out of these vectors. Now, how can we do that? If we recall that whenever we had a row vector or row matrix like this and we had a column matrix like this, then we could extract out a number. And in the bracket notation, we do the same thing. But here, let's say I can evaluate this number in two such manners. That is, one is like this. I can take the bra away and I can take what is similar to a dot product. In fact, it has a name of its own, which is called the inner product, but let's talk about that later. I first take this bra vector A and the ket vector V, and I want to have a number here. So the idea is the following. Now I just take the bra of it, 1 minus I, 0. And for the B ket, this is just I, 2, 0. And now if I multiply it, this is just I plus 2 minus 2I, and finally 0. So this is just 2 minus I. And we have a complex number. This belongs to the complex number set. Similarly, we could have used the bra of B and the ket of A. And if we do that, what is the bra of B? It will be minus I times 2, then 0. Not times 2, but the 2 is on the right side of minus I. And the ket for A is 1, 1 plus I, and 0. Again, if you multiply, this is just I, 2 plus 2I, 0. Oops, there is a minus sign over here. Yeah. So this is just 2 plus I. So we get a 2 plus I. And this is also a complex number. So we can see that whenever we multiply this bra and kets, like we used to multiply a row vector and a column vector, we can extract out a number. And this is similar to a dot product of vectors. In fact, this is called an inner product. And in bracket notation, we denote it as, let's say you are taking the bra of B and the ket of A. So you first write B, you put a less than sign over here, you give a bar, or that is a cell, or just a line in between them, and then you write A and this. This is something called an inner product. Inner product. And this thing is in fact a generalization of dot product. And because of this inner product, we can also get a notion of distance, or so to say the notion of a magnitude for a vector, no matter how abstract it may is. It can be a column vector, it can be a row vector, it can be a matrix, and many more. And here is an interesting fact. That is, let me choose to another color so that I can highlight it better. You can see that when we evaluated, let's write it again, the result, when we inner product with the bra of B and the ket of A, we got 2 plus I. And when we did the bra of A and the ket of B, we got a 2 minus I. Now this result suggests us that the number we are getting from BA is nothing but the Hermitian conjugate, or so to say the adjoint of AB. And this will hold always. So this is a very important relationship, and we'll dig into deep when we talk about the vector spaces and all that. Let's now try to see that how we can see Bra and Kets in a more general way, without just imagining the column and the rows. The idea is the following. let's say you have a matrix. Let's say I have a matrix called 1, 2, 3, 4. All the entries are real. It can be complex, but it doesn't matter. But for this discussion, let's just take them to be real. And I can actually decompose this matrix into the following. I can write 1 over here, and I can write 1, 0, 0, 0. Then I can write 2, I can write 0, 1, 0, 0. I can write 3 as 0, 0, 1, 0. And I can write 4 as 0, 0, 0, 1. This is just a decomposition, nothing else. And if we recall our index notation, we could have written this as, this matrix's components as Aij, right? The component. And here there is a very nice thing about the bracket notation. In the bracket notation, we saw that the columns and the rows, they were represented by bras and kets, or vice versa. But here in a bracket notation, the matrix A we would be writing as like this: summation over ij, and this small aij is, let's say, the components, and like this, that is, let's say, that is a bra of j and a ket of I. Now you might ask, what is this? What is this thing? In fact, it has a name, and it is called something called an outer product. And the way to and the way to see that this is something called an outer product, we will first we have to discuss vector space, and then we can define these outer products. So a matrix can be represented using this bracket notation. And if you compare these two decompositions, that is the decomposition over here and the decomposition over here, and if you write out this sum explicitly, you can easily see that this ket and bra thing, this will represent to these matrices, that is this one, let's say, or this one, or this one, or this one. Okay, and the way to do this is to run these I and j's from 1 to 2. Let's try to do it explicitly. So we are writing aij, ij, and we're taking a sum where I comma j runs from 1 to 2. So let's write this. First, take I and j both to be 1. If you write it explicitly, it will look something like this: 1, 2, a2, 1, 2, 1, and finally a2, 2. And now if I compare let's say this is my equation 3, and I want to denote this equation as equation 2. And if we compare equation 1 and 2, we can see that this a11 will be 1, a12 will be 2, a21 will be 3, and a22 is just 4. And this bra and ket 1, that is this guy, will be equal to 1, 0, 0, 0. And let's take 2, 2, it will be 0, 0, 0, 1, and so on. So this is the advantage of using the bracket notation, because the reason I'm saying this is an advantage, because when you look at this portion, that is this one, let's say you were given a matrix and someone gave them to you and they have written it like this, you can immediately identify the entries of that matrix just by looking at these vectors written in terms of bra and ket, where this ket guy represents the row number and this bra guy represents the column number. For example, this 1, 1 will correspond to the 1, 1 element in the matrix, this 1, 2 corresponds to the 1, 2 element, this 2, 1 corresponds to the 2 1 element, and this 2 2 corresponds to the 2 2 element that is on row 2 and column 2. So this kind of representation will make your life really simpler when you use them in quantum mechanics or quantum field theory, where you will have many matrices. Let's just say I want to evaluate some matrix products like A, B, C, and so on. Obviously there will be some conditions that will make it simplified, but let's not talk about this today. And in fact, we could have written, instead of this way, we could have written it in another way. We could have just written it let's just say another Ket vector. Let's just say Roman I. This is Roman number, and we could have written this as I2 or like this, and they would represent these matrices as well. So I discussed this example or demonstration just to let you know that whenever we think of Bra and Kets, yes, we can think of them in terms of row and columns, but they can also represent more diverse objects like matrices and sometimes even functions. So it's a good thing to keep in mind. And lastly, I would like to show something else. That is, let's say I do want to think of this Bra and Kets in terms of row and column. So let's say I write 1 as 1 0 and 2 as 0 1. Let's just say, why am I saying this? This will be clear when we discuss about basis, something called a basis of a vector space. And I just want to write it like this. Now I'm not justifying why I have written it like this, because it's related with the basics thing, and I want to get this 1 0 0 0 matrix out of this weird outer product. So how can I do that? So let's write 1 as 1 0, and so the bra of 1 will be 1 0, right? And I want to evaluate this. We already know that this is something we want as 1 0 0 1, sorry, 0 0. But how to get this matrix using these vectors? The idea is, first you write this Ket as this guy 1 0, and the bra as it's written on this side. And to do this outer product, what you need to do, you have to multiply each matrix itself with the elements of the other one. That is, let's take this one, this row vector or row matrix, and you have to multiply this whole thing with this element over here and with all the elements that appear on this column. Let me be explicit. So you write 1, then you write 1 0 this row matrix, and then you put 0 and you put 1 0, and now you just multiply them. And notice that there are 2 elements over here, so 1 will get multiplied with 1 first and 0 later, and at this point it's just a scalar multiplication. So this is just 1 0, and 0 multiplied with these 2 numbers will give us 0, and we have what we wanted. Similarly, if you do 2 1, that is 0 1 1 0, so 0 multiplied with this whole thing is 0 0, right? And 1 multiplied with this whole thing will be 1 0. Again, this is similar to what we have seen over here. And a final remark is that the elements of the vectors are either real or complex. So in general you can say they are just complex, because if you just take out the imaginary part, it's just a real number. So in general you can say they are either real or complex or imaginary, and you can comment so on. But the vectors are neither real nor complex. You see that this remark may be a bit odd to you, but we'll talk about it when we will look at the vector spaces. But this is a very important remark to keep in the back of your head, that the elements can be real or complex, but the vector itself is just a tuple of numbers which may be either real or complex. So this will be it for today, and I hope by this time you have placed this bracket notation at the back of your head, and from the next lecture we'll be discussing some formal stuff, that is vector spaces, subspaces, basis, span, dimensions and all that. I hope you'll enjoy it, and I'll see you guys on the next lecture. Thank you.